So in this clip, we're going to look at sort of two essentially different ways of modeling mass, but we'll see they're also kind of the same thing. So the first one is, suppose you have some material with a uniform density, but an uneven or irregular thickness, right? And so here, let's say the thickness is given by the graph of some function, and so I'll just do a little bit of doodling over here to indicate the kind of thing I'm thinking of. So we've got some sort of a surface like that. Okay, and then there's some sort of region that this surface is lying above, and so I'll just sketch that in here with some purple fill. All right, I wish I had those slick drawing tools where you could just like click and boom, it's all in there. But anyway, so this region here, this will be R. Okay, so we've got uniform density, and let's call the density rho. I don't know why rho is a common thing for density. And we'll call the thickness F. And then what we have is we have that the total mass of this object is going to be, well, the mass is always the integral over the region of the density. And so this goes up to a height of fxy, integrated with respect to some area element. Okay, so that's one way of thinking it. But then you could also imagine, like, what if you took some big flat surface like this and pressed down on it and just sort of mashed everything so that it was the same uniform thickness instead. And so then you might have something where, let's see, so based on the picture that I've drawn above, I guess the most dense region would be kind of here, and then there'd be some zone over here where it would be kind of almost as dense, and then less dense. And this is supposed to be like a sort of a cutaway view of the block here, so maybe we can see some of that action going on over here. And then there'll be like even less dense, and maybe the least dense region of all is kind of visible right here at the lowest part. Okay, so I'm trying to use color coding to represent the values of the density that we would get by just vertically compressing that block up above, right? So now in this case, what we have is we have a varying density. So now rho depends on xy, but we have a uniform thickness. And so this is, that height there would be C. And then this is still over the same region, so the total mass in this case would be the integral over R of now rho xy is the function we integrate, and C is just a constant for the thickness that we have. Okay, so we will use this idea of that the total quantity is the integral of the density many times. So the total electric charge within a region, when we get to like triple integrals, is going to be the integral over that region of the charge density. The total mass is going to be the integral over the region of the mass density. Right now I want to talk about probability density. So we will get to looking at center of mass, moment of inertia, and those kind of things in, what is it, 15.6, I guess. But until we get there and we start talking about triple integrals, let's just look at probability. Oh, and before we go on, let me just mention that it's of course possible to have both. It's possible to have a situation where you've got irregular thickness and varying density in the material, but that you can only deal with a triple integral. So we'll get to that later on. All right, so for now, I want to talk about the notion of probability density. So in this case, the color coding of the block above indicates just how likely it is that you have, like, it's much more likely that you have an outcome over here from your random event than an outcome over here in this part of the square. Or if you like this picture better, it's much more likely that your random variable takes a value here because the value is so high, rather than in a region of the same size over here just because the height is so low over there. So that's the idea of probability density. So we say that in one variable, if x is a random variable, so the numerical outcome of a random experiment, and I'll just denote this by RV from now on, then the way we model it is we say that the probability that x takes a value in a given set, so in other words, the probability that x ends up lying in this interval from a to b, you might see this written as the probability that the value of x is between a and b, like this, same thing. Then this is defined to be the integral from a to b of fx dx, where here this guy f, this is called the probability, if I can spell it, density function of x, and so this from now on henceforth will be abbreviated as PDF. So the probability density function, and so all we need to have the PDF satisfy, so that we're talking about probability, is we just require that it's always non-negative, because it doesn't make sense for to have a negative probability value. That's just nonsense. And we also require that the total integral of f is equal to 1. So here I'm integrating over the entire real line, or if that notation makes you slightly seasick, you can write it like this. But I prefer this one just because it's short and sweet. And I'm lazy. So okay, so some examples of how you model a random event with a probability density function like this. Now this, by the way, should all be review from somewhere in, oh gosh, I don't know, chapter 8 or something from single variable calculus. But so I'm going a little quickly here, but hopefully it's familiar. Okay, so let's look at the example of something which is uniformly distributed on the unit interval. So then the PDF would look like 0 up to here, and then it would jump up to 1 and go over to from 0 to 1, and then it would jump back down to 0 and carry on. Okay, so there's my portrait of f. So this is what we would describe as saying uniformly distributed on the unit interval. Okay, and the uniform there refers to the fact that it's flat. It's not weighting some parts of the interval more than others, like this one would. Any little sub-interval of, like if we pick something like this, or something of the same length over here, those are both going to have the same probability. Either of those two outcomes are equally likely. And then there's, maybe you're familiar with the bell curve from, well, people always use it when they're talking about exam scores and so on and so forth. If it's centered at 0, then the normal or Gaussian distribution looks something like that. Wow. Well, theoretically it would be symmetric and not look horrible. There we go. that one is worthy. I deem it worthy. That one came out rather well. Okay, so this is what we call the N01 or Gaussian distribution. Here the N means that it's called a normal distribution. I don't know why they use the term normal. It's just absolutely terrible. Then the 0 right here, this is the average or expected value, which we'll talk about, and it refers to the fact that it's kind of here in the center. I'll describe what I mean by in the center more precisely later on. And then this last part here, 1, that's a measure of the variance, or if you like to think of it as the standard deviation. So it's saying that the standard deviation is 1. And that's a measure of how spread out it is, as opposed to, something that looks maybe like this. Okay, so that's the Gaussian distribution. And then there's also another really common one that has some neat properties, which is called the exponential distribution. And so for this one, it looks like 0 up until we get to 0. And then it looks like a decaying exponential curve. Okay, so in general, it looks like e to the minus x, or more generally, lambda e to the minus lambda t for some number lambda, and this is called exponential. And the reason why we have a little coefficient out in front, and this reason why these two coefficients are the same, is because we need to satisfy this property that the integral of f is equal to 1, and so that's where that normalizing constant comes from. We'll talk more about that coming up soon. But this is all single variable, right? So we've got one random variable x, but it's very often the case that you want to study what's going on with two random variables at the same time, because you have two processes or one person going through two different experiences or something like that, and you need to be able to compare. And that's what we're going to be looking at in this section. So if y is also a random variable, then the way we model probabilistic events that include y is we say that the probability that the random pair xy ends up being in some particular domain, and so you would think of this being some region in R2. So it's like a randomly chosen coordinate in the plane, right? If you throw a dart at the plane, what's the probability that it lands in D? And this is going to be given by the integral over D of some probability density function now, which is the joint PDF of x and y. So it kind of governs what they're both doing together. And again, it has to have the property that it's non-negative, because negative probabilities don't make sense. And it also has to have the property that if you take the integral over the entire plane, then you should get 1, because that's like all possible outcomes.